Okay, well, 2 minutes after 10, I figure that's good enough. Welcome everyone who came today. I really appreciate that you're taking some time on your Saturday, whether it's in the afternoon, in the early morning, or in the dead of night. Today I'm going to talk about catalysis and transition metal chemistry. I actually have my PhD in this subject of transition metal chemistry. Got that in 1993. I have an abiding interest in this particular field. So I'm going to try not to be too technical, but I can get carried away. So if anyone has an animation of standing up and slapping me if I get too technical, then go right ahead. That might be kind of amusing. So without further ado, my little presentation on catalysis, with the conceit that Second Life is a wonderland. Okay, so lots of things can be catalyst. Notice I use the technical term Lotsa. Even really simple molecules like NO and NO2 can form a catalytic cycle. Right, so in the process of photochemical smog formation, what can happen is that nitric oxide or nitrogen dioxide, which are emitted by cars, comes out from combustion of fuels, with ultraviolet light. So in the middle of the day, these can split up, giving you an oxygen atom that finds a regular old oxygen molecule to make ozone. Now, that might be nice in the stratosphere, up in the ozone layer. It might be nice to actually make ozone and replenish it, but at the ground level, ozone's really bad because it reacts with volatile organic compounds, so stuff in the air. I mean, even trees put out volatile organic compounds, right? In the spring, everything that you can smell from that fresh spring scent, that's a volatile organic compound. It can react with ozone, making aerosol solids, particulate solids. Meanwhile, the NO will react with regular old oxygen again. Actually, two molecules of NO will split up a molecule of O2 and give you two molecules of NO2. And it's ready to go again. So a key part of being a catalyst is that there's a little loop in how you describe the chemistry. That basically a molecule will regenerate itself and cause something else to happen. Okay, so lots of things can be catalysts, and what I've shown you here in the picture over here, this is from NASA. It's basically ground level NO2 concentrations, and that's going to be a proxy for smog in the world. That was December 2015. So, I use the term organometallics. It sounds scary. It's not that bad. It's, strictly speaking, anything with a metal carbon bond would be a organometallic. And I mean metal in the chemistry sense, not the astronomy sense, where anything that's not hydrogen and helium is a metal, right? So, methane is not organometallic. So if it looks like a metal, shiny and electrically conductive, that's what I'm talking about, metals. Okay. Now, in practice, the chemists aren't so fussy. So anything that's got a metal carbon bond and is related in chemistry. So things with metal hydrogen bonds are count. And lately, things like with metal NO, because metal CO has almost identical chemistry with a few very interesting changes. Metal phosphorus bonds and a few others. Okay, so, keeping up with all these changes is kind of like a Red Queen's race. So, they're not organic metals. They're simply compounds where a carbon atom is bonded to a metal. And my favorite ones are transition elements, things like iron and chromium and cobalt, oh my. I'll show you some examples. So these things are rare in biology, so in your body there aren't many of them, but they're important. What few are in mammalian biology are incredibly important. Vitamin B12 cofactor over here, for example, usually has a cobalt carbon bond, and the carbon is basically methyl group CH3. This is really important because the chemistry of vitamin B12 cofactor involves the generation of adenosine radicals, which then go off and do something else. It's kind of nice to be alive, so having things like vitamin B12 cofactor, and there's the structure of it, looks kind of like the metal. There's the one little bond I care about, and then all sorts of organic cabbage, rest of it. Otherwise, things like nitrogenase. Here's the iron molybdenum nitrogenase. This little guy, where the pointer's quite fun. It's got a carbon atom in the center, and the carbon atom has 6 other atoms surrounding it. It's not violating the 8 electrons around carbon. There are 4 bonds around carbon rules, but it is 6 coordinate. It's kind of cool. I'd argue hemoglobin is a good example if you've got carbon monoxide attached, but it is a good example of the kind of compound that organometallic chemists are interested in. So here's another example. Old example, Prussian blue, compound discovered really in the early 1700s. It's blue. And you've seen this, you've seen artwork with this in. If you've seen Van Gogh's Starry Night or Hokusai's Great Wave, very famous paintings, you've seen Prussian blue. Well, Prussian blue has iron carbon bonds in it. Now, folks, if we're going to let metal phosphorus bonds and metal hydrogen bonds count for organometallic chemistry, then cyanide's going to count, Cn minus. So it's also used to make blueprints. That's kind of interesting chemistry. In this structure, and I've got a model of the structure. I'll pull it down for a second. Let's see. Edit, and we pull that down, and we don't crush the people in the front with our giant Borg cube. There's a structure of it. I've cleaned up this structure a little bit. Each vertex, so a corner, oops, let's turn that off. Each vertex or a corner represents an iron atom. And the iron atoms that have the orange lines attached to them would be iron 3+, irons with the gray lines attached would be the iron 2+. There's actually water molecules in the structure inside each of the little subcubes. I've got some slides on this, so let's move that out of the way. Up and away! Okay, escape, and all right, so here's the structure. This is crystal structure data, and so essentially, a side-on view is what I show on the very left. If you just kind of look at the cube from a slightly skewed angle, what you see is a little more complicated. In each of the little subcubes, there's a water molecule represented by the red sphere. We're not showing hydrogens at the moment. The structure on the right is just a stick model rather than the ball and stick model. And what you can see in the actual structure is that there's some disorder. There's some water substituted here and there for cyanides, which is why the bands along the edges look a little bit more colorful than they do in the structure that I just showed you, the 3D model and object in Second Life. I cleaned that up a little bit. Prussian blue. It's an organometallic. If you follow the strict definition where there's a metal carbon bond. So who cares? That's always a good question. Obviously Prussian blue is ubiquitous. It's just about everywhere. It's with all that cyanide, you'd think it'd be the most toxic thing ever, but the iron holds the cyanide in so strongly that you can ingest this stuff and not have particularly bad effects. In fact, it's actually used as a therapy for pulling out thallium or cesium if you've got thallium or cesium poisoning. It's got magnetic properties, and people are actually trying to use Prussian blues where you take an iron and substitute it with some other metal and make magnetic nanoparticles and attach drugs to them and use magnets to deliver these drugs to different parts of the body. So cool compounds. But moving on a little bit, if you're comfortable with iron cyanides, not that you have to be, and basically I'm showing you up here the Cn has a pair of electrons it donates to the iron. If you're comfortable with that, Cn minus is electronically almost identical to carbon monoxide. And that should make sense thinking about the chemistry of these things. Both of them can kill you, and they kill you in the same way. They would bind to your hemoglobin strongly and block oxygen from binding to your hemoglobin and essentially suffocate you. I showed you Prussian blue that has irons with 6 cyanides attached. Here's chromium hexacarbonyl. This one was one that's discovered more in the 1950s. Basically, it's got a chromium atom. It's got 6 carbon monoxides attached. This type of compound is a classic in the organometallic literature. Just so you know, I'm going to recycle this talk and use it as one of my first talks in my graduate course in the fall, graduate organometallic chemistry. So, I'm having fun here because this is going to be good stuff. This particular slide is a cross-eyed stereogram. Each of these molecules is octahedral, which means the chromium sits in the middle. There's a CO on top, on bottom, to the left, to the right, and one in back and one in front. And that's a very common structure. This octahedral motif is very common in the type of chemistry that we're talking about, the organometallic chemistry. Yes, you are helping to prepare my lessons. I'm really happy doing that. I just love being able to recycle the material. And the animations I'm going to show you later are actually going to help a lot with that too. So a long history, kind of the first one that it can be argued as a true organometallic, because people have issues with cyanide. They call it, oh, that's barely there. The first one was Zeiss salt. That's this guy. It's got a platinum. Platinum has 3 chlorides attached. This is square planar, so this is a flat molecule. And it's got an ethylene attached. I'll talk about how that attaches a little bit later. And basically, CH2 double bonded to another CH2. The whole thing is actually an ion. The whole thing has a minus charge. Now, in 1830, we hadn't really established that carbon was tetrahedral yet, so they did not know what they had made. But they had a reproducible procedure to make this stuff. It took X-ray crystallography, which started like 1905, 1910, to be able to figure out exactly what the structure of this molecule was. And I don't think that happened until probably the 1950s or 1960s. Has anyone heard of Grignard reagents? How do they determine the structures of molecules? That's an excellent question. If you can obtain a crystal of a substance, the crystal is a regularly is a packed array of the molecule with a repeating pattern. You essentially think of that as a diffraction grid. You pump X-rays in, you see where the X-rays diffract to. It essentially makes kind of a three-dimensional hologram. There are bright spots after you pump the X-ray through in three-dimensional space around the crystal. You find how bright they are, you find where they are, and you do lots of math, lots and lots of math, and can figure out what the structure actually is. It is like the go-to technique today. We do crystal structures on just about everything now. So, the Grignard reagent. Victor Grignard got a Nobel Prize for the Grignard reagent. I don't think it was called that back then, but in 1912. And these are a mainstay of organometallic chemistry, and many people actually make some in like their second year college orgo class and use them right away. They're essentially made by taking magnesium and some sort of a hydrocarbon that's got a metal halide bond, generally a metal bromide or a metal iodide or something like that, sometimes metal chlorides. This particular structure, the green is the magnesium. There is a chloride here, and here is a CH3. These rings up here come from the solvent, tetrahydrofuran. It's just there to help stabilize the magnesium. Magnesium is very electropositive, let's say. It doesn't hold on to electrons very well. It's got, I guess we should call it low electronegativity. Carbon is much more electronegative than magnesium is. So carbon is going to pull electrons in this bond toward it. Essentially, you treat this as CH3 minus. And that's going to be very reactive. Grignard reagents, when you isolate them, tend to be pyrophoric. They catch fire. Organolithiums, you can make the lithium analogs of these things. They tend to catch fire on exposure to air. They're very dangerous, and you really do need to be taught how to use them and well trained. People have died using these types of reagents. And you know, the fact that they are actually used by the tanker load in industrial chemistry gives you a lot of respect for the accidents that don't happen every day, and just makes it, when a accident does happen, much more horrifying. So, yay, accidents. That's one of the things about the organometallic chemistry. Metal-carbon bonds tend to be very reactive, and if you have enough of them around, if you have like large quantities around, if they generate a little heat when they react, the more you have, or more barrels of this stuff you have, the more heat you're going to get, and the more dangerous that you might get. Can such fires be extinguished with water or something different? The worst thing you can do to a Grignard reagent is add water to it, because it basically turns into methane, which catches fires. What we do to extinguish such fires, so if you're using lithium metal or organolithiums or lithium aluminum hydride or stuff like that, you need to smother it. You basically need to have a fire extinguisher that puts out a powder that smothers, gets rid of the oxygen. And yes, we have those in my lab. Ferrocene is a much more friendly molecule. This is an orange solid. You can heat it up to 500 degrees and it doesn't do anything. I mean, it's very stable. It was actually discovered in the 1950s, and the bonding in it is very interesting. Wilkinson, Jeffrey Wilkinson, was one of the winners of the Nobel Prize in 1973 for explaining its bonding. This compound is now a nice classic organometallic. It's even used as a functional group in a lot of organic chemistry. People have made unnatural amino acids out of it, and made weird DNAs and RNAs that incorporate this thing. It shows up everywhere now. There is a whole organic chemistry now to ferrocene. It's almost like a nitro group. Yes, I think if you replace some of the hydrogens up here with larger things, you can start gating the motor action. I think people have looked at some of those. So ferrocene is lovely. We have a lot of weird words in our in our field of organometallic chemistry. Ferrocene is an example of a sandwich compound. There are also half sandwich compounds where you've only got one of these little pentagons above, and you've got other groups down below. And in fact, I think I'll be showing you some of those a bit later. Let's see. Oh, gratuitous self-promotion. We put this structure out. This is a cobalt version of the ferrocene. The cobaltocene is what it's called. And so you got a little 5-membered ring sitting above a cobalt and another 5-membered ring. Iron and cobalt are next to each other in the periodic table. Cobalt has one more electron than iron. So for the cobaltocenes I've shown you here to be equivalent to or have the same electronic structure as the ferrocenes, the cobaltocenes have to have a +1 charge. Okay, so that actually came out Tuesday, I think, or last Tuesday. We put it out in a little structure report. It's not particularly significant, but it was a nice photo I had, or a picture I had ready for us. /1n. Okay, so catalysis. Most of the time when you're doing your second year organic chemistry class, you see catalysts, and they're just hidden over the arrow. PT for platinum or palladium or some other metal, and you don't worry about it so much. Just take your carbon-carbon double bond. It's carbon-carbon, anything with a carbon-carbon double bond is an example of a class of compound called an alkene. And with a double bond, you can break one of the bonds and attach hydrogens in their place. So this alkene is something that you would say is unsaturated, whereas the product over here is saturated. It can't take up any more hydrogen. So what I've just shown you is ethylene being hydrogenated by the platinum catalyst and hydrogen to ethane. It's a classic example. I was chair of my department for 3 years, starting in 2012, and we moved into new space. And some of the things that we got rid of from our stockroom were just delightful. We had, I think about a dozen 1-pound bottles of finely divided platinum on asbestos. That was one of the things I got rid of my first week, because that was pretty nasty. But it was basically no one thought anything of having such things. Some other time I'll tell you about how we found pound of thorium chloride and got rid of that too. So most of the time catalysts are hidden over the arrow, and transition metals make wonderful catalysts because they can bend the rules of the classic organic chemistry. I'm going to show you some simple catalysts when you put 3 reactions together. And Doesn't matter what they're really named, but I'm going to tell you the name. It's an oxidative addition, and that's basically when you take a compound, you break it apart, and you slam it onto the metal, the two bits. So basically the metal inserts into a bond in some other organic. What I'm calling insertion has a strict definition. It's basically when you've got groups of atoms attached to the metal, and one of these groups slides off the metal and onto your other group of atoms. That's what we call insertion. And finally, reductive elimination. It's a reverse process of oxidative addition. So two things that are already attached to a metal bond to each other and leave. Okay, so entry onto the metal, a modification mediated by the metal, and then leaving the metal. If you have those three steps in succession, then they can occur one after the other over and over again. So that's catalysts. Yeah, oh yeah, catalysts participate in chemical reactions, but they come back. Yeah, there's always a change in structure. I think they tell folks that they don't change their structure just because that's easier to explain than what's really going on. Things like finely divided platinum metal or finely divided metals in general tend to be catalysts, and for the bulk of them, there is no change in structure. But on the surface, there's all sorts of wonderful things happening. So, Wilkinson's catalyst. It's the same Wilkinson who's got the Nobel Prize. I never met him. My PhD advisor worked for him when he was a postdoc. So, basically, I've seen his handwriting. He used to write handwritten letters congratulating my boss on particularly nice papers that when they came out. But Wilkinson's catalyst is rhodium. And it's got 3 phosphorus-containing groups attached to it, and a chloride. And essentially, there's loss of chloride. I'm going to go through all of these steps in some detail. There's loss of the chloride, which gives you an open site. H2, a lovely little molecule of H2, can attach. A alkene can bind to the rhodium. Then we have an insertion step where hydrogen slides over, and we get rid of the double bonds, essentially. And then finally, the other hydrogen slides over, and it regenerates the catalyst. The work with these catalysts in solution have allowed us to figure out what's going on at metal surfaces. Yes. Surfaces do a lot of interesting things. So why do these steps work? Why does this work at all? One of the keys to this type of chemistry is having low oxidation state metals. So if you look at Wilkinson's catalyst, there's a chloride attached to the metal. The chloride's -1. All the phosphorus groups are neutral. They exist as, you can buy bottles of the phosphine compounds. So the rhodium only has a +1 charge. That's a fairly low oxidation state. There are wonderful compounds like the chromium hexacarbonyl I showed you earlier. It's the chromium in a 0 oxidation state, same oxidation state as in the metal. It's essentially single atoms of chromium metal. If you have plenty of electrons, you need somewhere to put them. And for the transition metals, d orbitals are available in space. They're big and can interact with things that come close to the metal atoms. Energetically available simply means that they have similar energies to where the electrons are on organic compounds. And in my class, I'm going to have to talk about transition metal chemists, how we count electrons a lot, because inventorying the number of electrons in a molecule lets you know something about its reactivity. I'm not going to bore you with that because that can get get harsh. Suffice to say that if you're comfortable with a carbon atom having 4 bonds to it, it means it's got 8 electrons, and it fills up the s orbital and the 3 p orbitals that carbon uses for bonding, right? So each orbital has 2 electrons. 4 orbitals make 8 electrons. Well, transition metals have those S and P. They've also got D. It makes a total of 9 orbitals available, which holds a max of 18 electrons. It's not as clear cut as for carbon, because carbon is one element, and the transition metals are like 30, 40, or I guess if we're counting the radioactive ones that can be generated one atom at a time or something like that. But essentially there's like 30 of them. So there are lots of exceptions. In practice, 18 electrons, 16 electron counts are very common. Those are the ones that hang around and are stable and can be put in a jar. Other counts indicate reactivity. And you also need physical space around a metal atom so that things can rearrange. Strangely enough, having an odd number of things attached to the metal atom helps the flexibility, helps things move around. If you have an even number, they don't move around so much. Let's see, \1 n. There we go. Fun fact, same guy. This is the same picture. And I think we're going to talk a little bit about each step in turn. Losing a phosphine is slow. These guys like to be what's called square planar. They're flat. It's wonderful from the organic perspective. From second year orgo, we do so much to teach students about how carbon is tetrahedral, how it's not just flat like you draw it on the paper. Then we have to kind of undo that when we're talking to them about the metal compounds, because some of them are flat like they're drawn on the paper. Here's some counting stuff, but essentially it loses a phosphine. There's the space and there's fewer electrons, so it wants to react with something when it's in this form. Okay, so we would call the starting material, Wilkinson's catalyst, it's actually a pre-catalyst, and the actual catalyst is that 3-coordinate species. It's got 3 things attached to the metal atom. All right. How does this work? Bonding. Bonding is the key. So metals have these d orbitals, and in the next step we're going to have hydrogen being split up into 2 MH units instead of an HH being attached. So if you think of this lower corner, lower left-hand corner is probably the best place to start. If you think of a hydrogen molecule, you basically got 2 electrons being shared between 2 hydrogen atoms. Metals aren't fussy. They'll take any pair of electrons anywhere and coordinate to them. Basically, in this particular d orbital, it can fit into the HH interaction and siphon away some of that electron density. That weakens the bond between the 2 hydrogens. And what's even worse for the poor hydrogen molecule is that the metal has these d orbitals. And I said if we have plenty of electrons on the metals can pipe those electrons into what are called the antibonding orbitals on the hydrogen. And antibonding orbitals do exactly what it sounds like. They negate the effect of a bond. So between these 2 interactions, hydrogen basically splits apart. Okay? I like to think about these interactions as like different channels of what's going on in the molecule. So if you think of a molecule like a TV, and you turn on your TV, you can see what's on, like, the PBS channel, and then you can see what's on the CNBC channel, right? And you might see different shows on each channel. Well, those channels like transmitted at different frequencies or different energies. And that's kind of the same thing that's happening here. These would be electrons at different energies. So on the left hand, we see what happens with hydrogen. On the right hand, I'm kind of showing you how a carbon-carbon double bond can attach to a metal. So here's the pi orbital that you usually think about, and it can glom onto the same orbital that the metal uses to filch some electron density from hydrogen. And then it has this, what we call back bonding happening into the alkene's antibonding orbitals. It gets really technical, but basically this interaction is responsible for just about everything I'm talking about today. So again, here's another shameless plug. I've got some 3D models up in the northeast corner of the Science Circle sim that shows you these interactions happening. I think I did it for nitrogen and for hydrogen as well. So, key thing, donation to the antibonding orbital breaks the HH bond. And if I'm right, I've got the Wilkinson catalyst model here, and let's bring it forward. Boop, 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 boop. I made an animation. It's behind the screen. Here it is. And we'll move it up. Oh, that's the wrong one. We'll look at that one just a little bit later. Right, I think this is the one. Okay, so this is this thing. Let me move it up a bit more. This object is supposed to be a Wilkinson's catalyst molecule. So I have a lovely tartan rhodium atom in the middle, and I've put some like toothpick things showing you the axes. They don't really represent the bonds. And for these triphenylphosphine groups, I have the little blue phosphorus atoms and these big old donuts that kind of give you a sense of how the space around the molecule is. And if I just click on this, we can see dissociation of a phosphine, and then the hydrogen came down, took its place, and starts to split up. And if that's all that's going to happen, whoops, then the phosphine would come back. We could isolate this dihydrogen compound. So that can play on a loop where we see the phosphine going away, the hydrogen being split up, and the phosphine attaching again. So that's how we might make a dihydride out of Wilkinson's catalyst. But if we actually have a olefin or alkene or something with a double bond around, then the phosphine just gets pushed out of the picture entirely, and the double bond attaches to the metal center. Okay, so I'll have that scripted object available up on the Mike's Chemistry Lab part of SCSim. I'll change the permission so that you guys can make copies. Yes, and I'm looking forward to showing my graduate students that particular animation. Okay, so back to the talk. How am I doing for time? So just going through what we did was I showed you all the different steps in the animation. There was the oxidative addition step. Well, actually, I haven't shown you this animation yet, but the oxidative addition step where where the hydrogen ended up being attached to the rhodium. Okay, And, there's reasons why the hydrogen would want to slide onto a alkene if it gets attached. So let's show you this animation. Okay, up, over, chunga. So essentially, in this particular animation, we've got the... move you over a little more. In this particular animation, we've got the phosphine already lost, and I've got an alkene ready to come in, and the H2 is just poised to break. So if we start it, the hydrogen is breaking. Then there's some reshuffling of things around the metal center. I'll talk about that in a second. And the alkene coordinates, a hydrogen slides off, and then we have reductive elimination. The next hydrogen slides off, and the hydrogenated molecule just goes away. And that leaves the catalyst in the right configuration to keep doing this over and over and over again. Let's see. Does the theory accurately predict the reaction rates? What we use to figure out mechanism is reaction rates. So the measurement of reaction rates when you look at H2 or HD or D2 or make other changes to the molecules basically allow us to make some conclusions about what has to happen during the mechanism. So let's see, we'll stop that. I think that's actually one that anyone can touch. I do get a bit worried about like how much memory these things use up. Okay. So a word we use is umpalum. And that's real. That's an actual word we use. It basically means that we invert the polarity of a functional group, invert the polarity of a compound, and change its reactivity. So when we bind the ethylene to a rhodium, it changes the reactivity totally. And instead of being an electron-rich species, it's electron-poor. The hydrogen is H minus because it's more it's seeking, it's more electronegative than the rhodium. So H minus and the H minus seeks the positive center on the alkene and then ends up binding. So let's see, that's the insertion step. And my animation looked pretty straightforward, but the thing is, the steps go backwards and forwards. They're reversible. There's nothing that really in each individual step makes the molecules like seek a particular direction, right? The loss of the ethylene, or I'm sorry, the loss of the product actually is irreversible, but all the other steps are reversible. This causes a problem, causes trans fats to build up. And essentially, let's say you have a larger alkene, methyl group, here's our double bond, methyl. There's no rotation around that double bond, so these guys are locked in place on the same side of the double bond. But once you attach to a metal, add a hydrogen, subtract the hydrogen, and pop off the metal, what the metal does is allows the cis versions, as we call them, where the methyls are on the same side, to turn into trans versions. This is a problem when you are taking oils and partially hydrogenating them. Okay, well, an oil and a fat are exactly the same thing as if you're a chemist. The only part that makes them different is whether you actually have some double bonds in. Oils tend to have double bonds. Here's a example. I got this off of Wikipedia. It's basically an example of an oil. And basically a polyunsaturated oil. Now we can add hydrogen to this. Oils are liquid because they don't pack easily. I redrew the same molecule, taking care to really emphasize how this structure is going to go. You can see that this molecule won't pack very easily because of the kinks that these double bonds enforce. Let's see, can you arrange reaction that... Yes, actually, you can do a lot of things, heating, cooling, especially if you get rid of a product, you can force the equilibria to go in one direction. Usually, if you want to take an oil and make it into something like Crisco, hydrogenated fat, you just have to use lots of excess hydrogen and make the reaction go to completion, and everything is hydrogenated. Okay. What happens is you get a small amount where you only get partial hydrogenation. So let's say I got rid of these three guys, and that straightens this thing out. Maybe I didn't get rid of this one. But I turned it into a trans. Now you can see that these guys are going to pack much better together as crystals, right? In fact, the trans fats pack much better together than the regular saturated fats. So this ends up accumulating in bad places and being, since it's unnatural, it's not something that's found in the body, being hard to dislodge. Artery wax is exactly right. That is a risk that we know about now from hydrogenating stuff. Final step, reductive elimination. So it's the reverse process, exactly the reverse process. All the same orbitals are involved. Why does it go? Well, there's an energy difference. The pair of CH bonds ends up being lower in potential energy than the combination of the double bond and the hydrogen-hydrogen bonds. So the energy for the restoration of the catalyst has to come out of the reaction. Yes. What a catalyst does is speeds up the reaction, but it doesn't actually change the energetics. So if you have a reaction that is unfavorable, so it's like you have to put energy in to make it happen, then yeah, you might have to boil the reaction or use photochemistry to make the reaction go. But if you have a reaction that is downhill, let's say, so like the one I just described here, then some of the energy goes into essentially resetting the catalyst. This hydrogenation does make heat, so it is an exothermic reaction. There is a lot of impetus for this reaction to go forward. So lots of variations on Wilkinson's catalyst. I'm thinking that this is going to be part one of a talk because I'm looking at the time here. I've got plenty of other slides. I'll show you my other last animation. Basically, I don't want to go like another hour over. So yay, less work for me in the fall. But let's talk about this just a little bit. Wilkinson's catalyst. There was a Nobel Prize awarded for this prep of L-DOPA. Here's the rhodium. The catalyst is a variation on Wilkinson's catalyst where the phosphines have a little more handedness to them. And what that means is that the hydrogens can be added to these two sites so as to prefer a particular handedness to that carbon. L-DOPA, the L basically stands for levorotatory. If you pass plain polarized light through a solution of L-DOPA, the light will rotate to the left. That's something that Louis Pasteur knew about in the 1860s. If you just use regular Wilkinson's catalyst, you'll get a mixture of the left-handed form and the right-handed form. I don't know if the right-handed form is useful for anything or if it's even toxic. So this is one of the early examples of how this type of chemistry operated to benefit the pharmaceutical. Let's see, /1. Where are we now? So gratuitous cat photos. Okay, so obviously, obviously I've got my cats. Albert, Seth, another one of Seth. This is Ishtar. She's new and she's large. I talked about Tori last year, and he passed away. He actually had a bowel cancer going on. After we cured him, yay, of the oh, I've even forgotten the name. We used nuclear chemistry to do it. I didn't do it in my lab. We took him to a vet. So let me get and see if I can get to. Okay, so carbon groups can also slide along metal carbon bonds. Hey, what if instead of reacting with a hydrogen and going away as ethane, had another ethylene? We had more insertions happen. We can make ethylene into polyethylene. Early catalyst for that was the Ziegler-Natta catalyst. You can do this purely with organic chemistry, but you get low quality polymers out of it. Ziegler-Natta basically starts with chromium trichloride or some other transition metal, some trimethyl aluminum, that's kind of nasty pyrophoric stuff, a little trace of water, and then ethylene will turn into polyethylene. A catalyst, that I hadn't thought of, but it's really funny. So, let me edit, let me bring this guy down. Boop, 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 boop. This is an example of what's called a ANSA metallocene. ANSA because the two cyclopentadienyl, the two 5-membered rings on the top and on the bottom are attached to each other. The pink atom is zirconium, the greens are chlorides. This is a crystal structure from work by work out of Caltech in 2006. This wasn't the best catalyst, and what by best I mean, I'll explain that later. But basically, this was one that allowed them to figure out what was going on. Let me show you the animation that I've got. It's a little less polished. We'll bring this guy up front. So, what I've tried to represent here is propylene. Let me move that just out of the way for 1 second. So propylene is an alkene. It's got 3 carbons. There's a CH2. There's a CH2. Hello? Yes, a CH and a CH3. And the thing is, when you string these together into a polymer, where I've got the laser pointer, that carbon ends up having handedness to it. But if you have 4 things attached to a carbon and they're all different, and you put the smallest one in the back, like you look at it from a perspective where the smallest one is in the back from you, you can figure out 1, 2, 3 from biggest to smallest. If you go clockwise, that's one geometry. If you go counterclockwise, that's the opposite handedness geometry. So for metallocene polymers, what we like to do is have these alternate. Like left-handed, right-handed, left-handed, right-handed, left-handed, right-handed. And there's a name for that. It's called syndiotactic, I think. Hey, let's show the zirconocene animation. And then maybe we'll call it quits there, and I'll answer any questions, and then we'll have a second part to this. All right. So starting, I've got on the, let's see, on the right, facing the screen, from the pink atom, going off to the right, I've got a CH2, and I've got a big green donut. That represents the growing polymer. From the pink atom over to the left, I've got a propylene attached. And it's not quite a perfect representation. I'm hoping no one calls me to task for it, but at some point the propylene is going to attach. The idea is that this bigger group, the big blue sphere, is going to try and nestle in this catalyst so that it's got space. So what should happen is that you get an insertion, and then another insertion, and then another insertion. And I've got this on a loop. I tried having another insertion, it keeps crashing. So, but basically a polymer can be built through multiple insertions as the zirconium just shoves propylenes into this growing polymer chain. Okay, if I stop it, what you can see, and I'll have this set up in the Mike's ChemLab region of SC so that you can play with it as well. What you can see is that the handedness around the alkene or around the polymer groups does alternate. Okay, so with that, I'll just kind of fast forward to some acknowledgements, and there's other slides, but I'll use them in a talk this summer. Let's see, so let's go to /145. Will that work? Yay! We'll move this guy back out of the way. So, where do I get X-ray data from? X-ray data is wonderful. There's 4 databases that I know of: Crystallography Open Database, the RCSB Protein Database, Cambridge Crystallographic Database. You have to know the reference to get the structure for that guy, and the American Mineralogist Crystal Structure Database. Each one of these has either several hundred thousand X-ray structures, or getting up into the millions of X-ray structures. You can download it's called a crystallographic information file. It's just a short text file, and that can be opened in JMOL to show you the 3-dimensional structure. And JMOL will allow you to export this as an X3D file into Blender, which you can do a little bit of cleanup on it. Save it as a DAE file, which you can upload into Second Life as a mesh object. We're also using Unity with a Google Expeditions kit. I'm sorry, I had to turn around and look at it to show these structures to our students. So I'll actually show you more about that stuff this summer as well. And finally, some acknowledgements. Thank you for your attention. Obviously, the Science Circle is growing, and we're trying to do some more fabulous things. We'll be telling you about these shortly, I think. Thanks to NSF for their support for my research, students that I've worked with, George, my collaborator over at University of Oklahoma. SIUE has been very supportive, and of course all of you for your attention and continued support of the Science Circle and Second Life. Alrighty, and I'm happy to answer questions. Let's see, is propylene planar? Yes. And sorry, Syzygy, about the flying molecules. They're very small, so they wouldn't really hurt if they hit you in the head. Well, they'd probably catch fire too, but yeah. Catalysis, yes. Apparently Watson and Crick used X-ray crystallography to determine the structure of DNA. Yes. They could tell there was a helix, but it took a while to determine that it was a double helix. Yes. You know, we've come a long way with X-ray crystallography. One of the first crystal structures, and forgive me if I get the date wrong, I think it was like 1905 or 1910. One of the first crystal structures was sodium chloride. And essentially with sodium chloride, it's just cube, think of cube, sodium's at one vertex, chloride's at another vertex. Very, very simple structure. But, they fired X-rays into their crystal, and they actually had to take photographs, photographic plates to cover the three-dimensional space in 360 degrees X, Y, and Z, and also moving out from the crystal itself to a radius of, I don't know, a reasonable radius might be about 40 centimeters or something like that. They had to take probably thousands of photographic plates. And on those plates, they had to basically, by eye, estimate the brightness of each spot that they found, put all the data together into today we'd call it a file of X, Y, and Z coordinates of each spot and how bright they are. They were doing all of this by hand. So all the calculations took 5 years to do the calculations and come up with essentially the same crystal structure that today we can do in about an hour. Yeah. The advances in crystallography are just amazing, especially in the last 20 to 30 years, where we've been able to get crystal structures of proteins. Crystallizing proteins is not an easy thing to do. And in fact, advances in using synchrotron radiation to get the data that you need within seconds almost allows you to put a snapshot, a series of snapshots of structures together to see changes happening in real time in proteins. Rosalind Franklin. Yes. Rosalind did not get much credit for her contribution. That is very bad. So, yeah, crystallography has a long history. These days, the crystallography is almost a routine technique. I kind of, my boss. Well, my advisor kind of always thought of crystallography as the technique of last resort, and that you'd use the sporting methods like the NMR spectra, the infrared spectra, the cheap methods, in other words, to figure out the structure of a molecule before you resorted. But in those days, it was data collection took 7 days, and the computers even up to 1993 took several days to actually process the data. So, yes, without that, DNA was not possible to be produced in 3D form. Yes, the 3D structure of DNA should be attributed to Rosalind Franklin as a triumph of science. Base pairs turned outwards. Yeah, that would be awkward. That would be awkward. Yeah. And that's funny considering how much he knew about hydrogen bonding. Because, the base pairs are hydrogen bonded to each other. Hydrogen bond is like 1/10 the strength of a regular carbon-carbon bond. But between each base pair, you've got 2 or 3 hydrogen bonds, and you've got thousands of base pairs. So those lovely hydrogen bonds are just strong enough to keep everything together, but it can still be unzipped, replicated, and rezipped. Yes, dative bonds. Very much important in this field of inorganic. Yes, and I think in a lot of the crystal structures of protein molecules and of enzymes and of DNA, we focus on the organic parts of it, but there's always a lot of water packing in the spaces that actually helps keep the tertiary and quaternary structures in place. Yeah, the hydrogen bonding in water is responsible for a lot of its anomalous properties. Right, because if you look at H2O, H2S, H2SE, oxygen, sulfur, and selenium are all in the same group, but water has a boiling point that's like, I think, 150 degrees higher than H2S boiling point, right? H2S is a gas. It's because of the hydrogen bonding. H2S doesn't do the hydrogen bonding nearly as well as water does. And ammonia has the same thing going on to a lesser degree. Desiccation disrupts tertiary structure. Yes. Yeah. If you have, remove waters that are holding hydrogen bonding different parts of the protein together, there's going to have to be changes. And I think usually what happens with proteins is they just kind of crumble up and denature if you take all the water away. Dust to dust, yes. Yes, absolutely. So everything I talked about today for transition metals actually holds true for enzymes, and some enzymes use transition metals as their active sites. Some enzymes use just purely organic sites as their active sites, and really they if you were to call an enzyme a nanomachine, that would not be inaccurate. And yeah, DNAs and RNAs are now known to also be able to support some catalysis. Yeah, metal. Yeah, lead is bad. Lead is really bad. I mean, there's not a lot of sulfur in, comparatively, not a lot of sulfur in the human body, but where the sulfur atoms are, they've got jobs to do. It's really important. And things like lead and mercury really like sulfur and bind to sulfur and just block those spots. Yes. Do I have a landmark for the lab here? Let's see. Let me see if I can do that. Okay, well, I'll let Chantal do that. It's just off to the northeast. Yes, Mendeleev. Yes. Yes, all the transition metals, the whole periodic table and its structure starts, the accurate depiction of its structure starts with Mendeleev. Yes. Very cool. Well, if there are no further questions, I should probably log off and return home at some point, play with my cats, mow the lawn, um, and I've actually got my idea for the next presentation. I'll talk a little bit about more polymerization, because there's Nobel Prizes that I didn't get to, like the Grubbs catalyst. I want to talk about that, and if I do one in the summer, I'll make a animation of a Grubbs catalyst. So, yay! Oh, okay. Let me see if I can figure out which slides are there. Da, 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 da. So I did the Mad Tea Party. Um, Let me show you that slide. Backslash 134. Whoops. There. Sorry, I forgot the one. And essentially, the catalyst can control the geometry. You'll notice I do have my Catalysis and Wonderland theme here, head to head, where the CH2 groups bind together and alternate that way is uncommon. But there's all sorts of ways that a catalyst can put the molecules, or the molecules of propylene together. If an enzyme targets this chain, how will it cut? That's the problem. An enzyme's going to have a rough time cutting this sort of chain. Most enzymes, when they cut polymer type chains, will look at peptide type bonds, or CO or CN bonds. These are CC bonds, and that's it. Breaking them is a big problem. Oh, I would love to hear about this. There is one of my conclusion slides that's important here. Because all this chemistry I talked about today, the polymerization is nice, but then we get plastics and people throw them out instead of recycling them. We get the trans fats, right? So I kind of felt a bit sheepish about some of the topics today. So basically, we have a lot of plastics in the. Oh, I'll talk about that stuff. I'll talk about next time. But yeah, basically, if there are bioenzymes that can chew up plastics and turn it back into starting materials, things like oil, then that is awesome stuff. The specific catalysts I talked about, since they're so air and moisture sensitive, are bad at undoing what they do. So Sumatra 1986, that would be lovely to chat about. Awesome. Cool. Okay, so so at this point I will kind of go offline. I think I will reply to a couple of people who've talked to me. Let's see. awesome. Yes, send me stuff at a later stage. That would be awesome, and I'll definitely answer. And also bring your questions next time I talk, because we'll continue on with this theme. Oh, no problem. No problem. I've taught freshman classes with over 200 people in, and you get used to people knocking you over as they find their way to their seats when they're 30 minutes late. I've gotten very forgiving in my old age. Alrighty. Yeah, I'm going to have to head out. So thank you all for coming, and I'm going to log off now, and I'll clean this stuff up in middle or toward the beginning of next week. Thanks much. Bye, everyone.